Welcome. Let's talk about multiplication. So we've done addition and subtraction. In reality, multiplication has a couple of different ways to kind of look at it. The most basic way is actually repeated addition. This is often introduced to a lot of students by counting by a specific number. So for instance, in elementary school, it's a common thing to say, okay, let's count by twos. So you go two, and they go two more is four, two more is six, two more is eight. And that is actually going through the multiples of two. Two times one, two times two, two times three. Especially count them on the fingers. So before you even tell them they're doing multiplication, you can have them doing it by this repeated addition model. So in this way, it's really, really good. And this actually is a common thing. Another really cute, cool thing that I'm seeing a lot more these days is the area model. Specifically, the area model is kind of constructing and making a grid or looking at different ways that we can actually count area using dimensions. This gives a visual effect of students to be able to see what multiplication is giving them. It's a really cool thing, and it kind of helps. A lesser one that's used in elementary schools is what's called the Cartesian product, but it makes sense when we start thinking about how to compare and build some things. So again, let's go through these three different models. So that's repeated addition, the area model, or let's call it the Cartesian model. So the repeated addition, 3 times 4 is 3 added up 4 times. So 4 of them. This again is really cool because they often count this on the fingers. They hold up one finger, they're like 3, and they go 3 more to 6. Hold another finger, 3 more is 9, and 3 more is 12. So in this way, they can do it. It's very easy. And again, counting on your fingers that way, not a bad way. Gets them introduced to this idea and really helps it feel familiar. To see this a little bit different, let's look at a visual effect. So here we have a block. Specifically, I'm going to use this top block in which we have 4. You notice I have 5 4s, and in this way. Now the top block really should be split up, and it should be split up so that we have this. So that's actually a 5 and a 5, and I can split this 10 up into a 5 and a 5. So we can really see that this is 4 5s or 5 4s, which gives the idea of multiplication where you can multiply in any order. 2 numbers multiplied together, you can do it in opposite orders. Again, down here, you can count this on a number line. I actually see my own children. It's a common practice is where they're given number lines, and they simply go along the number of ticks, and that's one block. And they go next number of ticks, and that's the next block. And how many blocks do they move along? So this idea is kind of useful, it's kind of interesting. The general definition from your book, it looks like this fancy n, where n is just how many times you're adding up that number, times a, and it's kind of, this is a general thing. Again, this is the very abstract notation. I'm not going to pout it on you, but so you know what it's actually talking about. Now let's switch to the area model. So 4 times 5 and 5 times 4 is kind of cool. So if you look carefully over here on the left-hand side, we have a bunch of dots. Now notice I can count them as 5s, rows of 5s, and I got 4 rows of 5s, or I have 5 columns of 4. So in the same way over here, when they're blocks, instead of having the dots, we're counting the blocks. Same idea. So this again helps illustrate the idea that a number times another number can be switched and you still get the answer. So 4 times 5 in both these, they can just count the total number and again get 20. Well, the Cartesian model, let me just kind of explain it with an example. Suppose I have 2 classes that you're taking. One's world history, one's ancient history. And let's suppose you have to take another class that's in some language, Latin, French, or German. So how many ways can we do this? We're going to use what's called a tree diagram to see the number of ways. So to kind of explain this first off, we'll call H the number of history classes that are optional. We got 2 of them. And we have 3 different language classes. So using this kind of cool thing, or if you look at it from this standpoint, let me get my little spotlight. I break off my schedule. I first pick which of my history classes. And then I have 3 options for each of those. And that gives me a total of 6 options. Notice where it's 1 history class and 1 language class. So this is how we can do this visually to see this Cartesian product and understanding that really when I'm multiplying 2 things to get different combinations. Now, the interesting part is how many things were there in the history? Well, there were 2 things in my history. And how many things were in my languages? There were 3. And thus, we can quickly note that 2 times 3 is 6. So we had 6. It's called the fundamental counting principle. I'm not going to pound you on that one. Actually, more commonly, it's just called combinations of things, how to count the combinations, and so forth. Now, I'm going to go through a couple of key properties of multiplication. Again, these are important for you to know because actually they're part of something that we teach children, and they do occasionally show up on the content exam. First, closure of properties, meaning if I multiply 2 numbers, if I multiply 2 integers, I get an integer. If I multiply 2 whole numbers, I get a whole number. It just keeps it in the same kind of number. Again, there's lots of different kinds of numbers out there. There's whole numbers, integers, real numbers, rational numbers, and of course, probably your favorite, imaginary numbers, which are part of complex numbers. But my biggest part is when I multiply 2 numbers, it still gives me a number. Multiplication is great that way. No matter what the 2 numbers are, the product of those 2 will always give me another one. Now, that probably is a little bit confusing, but it just means I get to play and do some extra properties. It doesn't matter if I multiply anything. The commutative property, commute means to move, meaning I can move the order and it does not change the number. Similarly, the associative property. Now, what's association? Well, it's your association when you're connected with something. So if you look at this, A is connected to B. We do that multiplication first and then C, or A is multiplied by BC after BC is multiplied first. Again, this is what computers and calculators do. They do not actually do all 3 numbers at the same time. They are actually executing the exact same methods that we talk about, but in some variation. That's actually why computer programmers have to learn a lot of math, because they actually have to program in the most efficient program, which, by the way, is not usually the standard algorithm that many of you have learned different things. It's usually some other methodology. All right. Now, one last thing just to point out is the identity, pretty much that any number times 1 is that original number. And I will also throw one last one. Any number times 0 is 0. And this makes sense when you do repeated addition. If 1 times 3 is 3, 2 times 3 is 6, because it's 2 3s. If I have 0 3s, then I have nothing, so I have 0. So that hopefully makes a little bit more sense, and it's kind of a hard thing. Even my son, who's going to the 5th grade, asked me today about this because he got up this mixed up division, which we will get to later. But just focusing on multiplication. All right, so let's talk about commutative property. Again, commutative property makes sense when you look at it from the standpoint of these are the same areas, but I just rotated them. So if I'm reading this as the leftmost number times the right, the left, this number times this number is 3 times 5. Well, this is 5 times 3, but it's the same thing, just turn your head on sideways. So because of that, that's perfectly fine for us to understand that. What about this? Well, notice here I'm doing 3. I have 3 of these stacks, but I'm multiplying the 5 times 4 first. So I'm multiplying this and getting this brick, and then I'm doing 3 of those bricks. So that's 3 times 4 times 5 times 4. Similarly, I could have done the 3 times 5 first, boom, and then I would have had 4 of them, and I combine. This whole combined like cube shape is going to be the same either way, because it has the same 3 dimensions. I'm just rotating and deciding if I'm cutting it horizontally or vertically in order to kind of break it up into the smaller chunks. Now, for association, for distribution, you kind of can see this. 5 times 3 times 4 is really do 5 times 3. Change to my drawing. 5 times 3 is going to give me this chunk. And 5 times 4 gives me this chunk. And they have them broken out over here. But because I have the same total amount, I can distribute that. And instead of doing, I could have done 3 plus 4, which would give me 7. And 5 times 7 is 35. Or I could have multiplied 5 times 3, which is 15, plus 5 times 4, which is 20. Again, we get the exact same value. This is a great thing to have elementary school kids actually play with the numbers and see that they actually match up and verify for themselves these properties. But they're not just some magical property. The idea is simply that we can distribute, which means we can multiply into parentheses if there is addition or if there's subtraction. And this idea is actually very, very important, especially when we start talking about order of operations and some other aspects that we'll get to later. Now, the distributive property works on both sides of multiplication. So instead of the summation being on the right, if it's on the left, it still works. Also, if you have 3 numbers being added together, we can do this. Now, another way this comes up is not really an elementary school idea, but I'm trying to set the stage for you to understand how your teaching actually impacts students later. If your students understand distribution, then doing what's called factoring makes more sense because factoring is undistributing. It's unmultiplying something. That's how I often actually explain it when I teach it, and students are often in shock because they never realized, or because they have issues with their distribution properties, which is just basic arithmetic, causes massive issues. So understanding this is how you all actually have a massive impact on students in their performance in both middle school, high school, and beyond. So believe it or not, you all actually lay the foundation. And if you don't lay it right, it actually causes lots of problems for the students throughout the rest of their careers. And sometimes students take themselves out of a career because they simply think they can't do math that is necessary for that career. All right, so let me do an example real quick. And I know this is X's, Y's, and Z's. This is the classic for distribution. It's written out this way, and this is sometimes called FOIL, but to understand what you could have done is this. Now, let me demonstrate with my little fancy little highlighted. If you look carefully, this first top, actually, let's do this is really X times Y plus Z. So I took the X and I multiplied it into all of this. And if I do that, it's going to actually give me an interesting little quality, namely that I then can actually produce a new way of writing the summation. So I actually now have, I can actually write this, sorry. I can actually write this as, my device will actually start working. Okay, I can write this now as X times Z plus W plus Y times Z plus W. And that's because we have the top one, and then we have the bottom one down here. And then we can again distribute, the X can distribute to both of those, the Y can distribute to both of those, and that's how we end up with this total. So this idea of FOIL that everyone wants to talk about, it's a really cool acronym, is really just distribution. So again, as you teach this in your classes, you get to have a wonderful example and kind of set it up there. All right. So I'm going to hit one last idea about exponents to make sure you kind of understand where we're going to go in totality of this class. And that is namely, we're going to talk about multiplication by going to exponents. So exponents are simply repeated multiplication. Hopefully you already know that. And again, we're treating this as if the exponent is not 0. 0 is a special case, and there's some more things. So anytime, if I'm saying a squared, that really means A times A. If I do A cubed, it is A times A times A. Now you all notice I generally use these dots instead of the X for multiplication. That is in part because the X can cause massive issues when students move on to algebra, which is becoming a bigger part of even elementary school, per TEKS and Common Core. All right, so we have this first property, which is simply multiplication is multiplying something out. Now, from there, we can build a couple of interesting things. Now, I'm going to point out why these things are this way, because hopefully they make perfect sense. So this first one, I'm going to do an actual combination. I'm going to use A squared times A cubed. Well, A squared is A times A. That is A squared. A cubed is A times A times A. There's three of them. Are you okay that A cubed is this, A squared is this? Well, based on our definition, I have 5 total A's, so that's A to the 5th. And we know that 2 plus 3 is equal to 5. So that's why if they have the same base, we just simply add the exponents. Now, on the other hand, this one down below, if the exponent is on the outside of parentheses, so let's do A squared cubed. Well, what that means is I have A squared times A squared times A squared. And when I multiply these, I'm going to use this property up here 3 different times, which is going to be A times 2 plus 2 times 2 plus 2. But again, when we just talked about for multiplication, that's the same thing as A of 2 times 3, is repeated addition. So these are where these ideas come from. And the truth is you can build on it and help students understand that so wonderfully. All right, I'm going to end there. Please let me know what questions you have about multiplication and exponents.